First thing, just to kind of get started, log into the supercomputer. So we're kind of ready to go with that a little later. And I want to go over something that's very important in molecular simulation. I got it drawn here. There's something called the virial theorem. And it has nothing to do with the virial equation of state. That's the tricky part. Well, but it's kind of related to similar properties. It tells us how we can calculate pressure from a molecular simulation. And so this is what's called the virial theorem. And you can actually search online, and there's all sorts of web pages. There's a Wikipedia page on the virial theorem. So if you want to, you can do that. I don't want to prove it. I just want to explain this is how we calculate pressure in a simulation. You'll notice here, this is just the ideal gas part. And PV equals, NKT. And if N is Avogadro's number, then you could do RT. But then the non-ideal part is what the virial theorem states. And you'll notice that you dot the position of the particle into the force on the particle. And remember, the force and position are vectors, so it's a dot product. And you have to do that for all the particles, and then you take the ensemble average of it. Remember, this angle bracket is ensemble average. Now in simulation, what we do is we do this calculation while we're going through the loop. You can prove, notice that this is on particle I, force on I, but forces are all related to other atoms, right? You have force on particle 1 from force on particle 2. And you can relate that to then the loop you would do to calculate the forces by just summing up all the distances times their components and the forces. In the same loop, you're doing the energies or the forces. So to save time, rather than make another loop where we do this to calculate the pressure, we calculate the pressure in the same loop where we're doing all the energy or force calculations. And it comes out, we already have calculated we've already calculated the distances between each of the particles, so we don't need to redo that. And then we can just calculate the forces. And so we're going to need the forces to calculate the pressure. That's kind of the bottom line. Any questions on this? I'm not going to prove it again. You can look it up if you want. It's called the virial theorem. It has nothing to really do with the virial equation of state. No one really knows where the term virial came from, but they think it's kind of, I think it's a Greek word that has to do with something about pressure or space or something like that. Okay, that's the first thing. We want to calculate pressure. It's one of the very important things in simulation, right? If we're getting the pressure, volume, temperature, the PVT properties of a compound. In the simulations we've done so far, we specify the density or the volume, right? The reciprocal of the volume. We specify the temperature, and then we could see what pressure we get. And we'll see today we can actually do vapor-liquid equilibrium and set the pressure. Okay, now that I've given you a chance to log into the supercomputer, I'm going to show you how. We're going to do a little bit on the supercomputer and then come back to another part of our lecture. Let me switch computers real quick. Get my code for the supercomputer. I thought I was logged in. So you should see my shell. And let me just kind of adjust my screen a little bit so you can see it all. Okay. Oh, you sucker. Sorry about that. Okay. Can everyone see my screen?
Yes.
Okay. So I helped several people. I hope everyone's kind of up to speed on some basics of navigating the supercomputer. If you want to, you can also, I think some of you using Windows are using WinSCP to edit your files. So you can open that up, get that all connected so that we can edit some files. There is the FSL groups. I want you to change into the FSL groups folder. So CD FSL groups, and I'm going to list that for me, LS. And the one you're going to have is FSLG and then underscore Chemi 513. So I'm going to go into that one. You can notice that as I'm typing, I hit tab to autocomplete. I told several people that. So if I type FSL and hit tab, it'll autocomplete as much as it can. And then I put capital C, and then it was able to complete the rest of it. So if you list the directory, I have put in there a couple things. So the thing I want to look at is this submit.sh. When you want to submit a job to the supercomputer, you have to create some sort of script. You don't have to call it submit.sh. I just called it that. You can call it whatever you want. But I'm going to open this up. And I hope you can see the colors here, but this is a script that you're not going to quite understand. In fact, if you can actually generate this script if you go to the supercomputer website and you go to job script generator. You can tell it all the options you want, and then you can see down here, this is kind of the script that it's making. And so let's just walk through a little bit about what this is. Can you see the text on my, it's kind of like a pale blue or something like that, a turquoise. Can you guys see it? Let's walk through it then. You have to have this little top line. This means it's going to run using bash script. It's basically a language, bash shell. And that doesn't really need to change. Just need to have it there. And then the job scheduler that the supercomputer uses is called Slurm. It's a terrible name. I don't know why it's called that. They've changed over the years. Sometimes they used to use PBS. Sometimes they used to use, there's all sorts of job schedulers out there. The one they use is Slurm. And then you have to give it a bunch of Slurm commands. Let me just check the chat. I saw a few people. Oh, you don't think you can open? If you want to, Legrand, let's quit this. So why don't you, in fact, let's do this. Here's the command. I want you to copy.
I figured it out. It just have to be read-only, I think.
Yeah, you can do read-only. The other thing we can do here is, let's go CD. Let's go back to our home directory before we start looking at the submit script. Notice that there is this compute. So if you type CD and then hit enter, it will take you to your home directory. CD, then enter. There's a compute directory where you want to run all your jobs. This is fast disk space on the supercomputer. You don't want to store their stuff there long term, but this is where you run your jobs. So what we're going to want to do is we want to go into, so CD into compute. This is where the supercomputer has said, we want you to put your stuff. And notice that I created this, I have this LJ folder. Now you can create whatever folder you want here. Now, so I want you in your compute folder to create something. So mkdir, and then you can create whatever you want. You can call it LJ, you can call it test, you can do whatever you want. So mkdir LJ, that'll create a directory. And in my directory, I already have a couple things. I just want to, so the way I've got my nomenclature, you don't have to follow this nomenclature. The way I've done this for this Leonard Jones is I tell it how many particles, what the dimensionless temperature is, and what the dimensionless density is. So this N500 T085 R09, that means I've run 500 particles of Leonard Jones at a dimensionless temperature of 0.85 and a dimensionless density of 0.9. So I'm going to go into that one, N500 T085. And I've actually run both MD and MC, but the point I'm going to show you here is what you have to do is create a submit script that tells the computer everything you want to do. So I'm going to open mine up just for a second. We'll talk through it. And actually, what we want to do is let's copy. Let's do this. Hit CD, go into the groups. Go to your Chemi, and I think I got this all set up to LJ test. We're going to copy. So I'm going to print work. So you want to, from your main directory, go into your groups and then go into FSL groups, Chemi 513. And there's this LJ test. We're going to copy this into your compute folder. And so let me just show you the command to do that. I'll pause right here for a second. I want to make sure everyone gets here. Copy, CP is copy. -R is needed because you're copying a whole folder. You just kind of have to get used to that in Linux. Is if you don't put the -R and you're trying to copy a folder, it'll say, oh, it's not a file, it's a folder. You got to use -R basically. -R means recursive. So it's going to do the folder plus everything inside it. So CP space -R space, we're going to copy LJ test. I've already set up some things for you. And you're going to put it in the compute folder. And that little tilde that you see, which is next to the 1 key, shift next to the 1 key, it's like a backwards accent or whatever that is. Then that's saying go to your home directory and then go to compute. And so I'm going to copy this LJ test into compute.
Where is LJ test?
So it's in your group folder. So here,
FSL groups.
Yeah, so FSL group. So I'm going to start in my home directory. You won't have all this junk, but notice there I'm in FSL groups. I'm going to go to FSL groups and then FSL groups chemical engineering. So you can go into here. Who's not there? Who doesn't see LJ test? And I can help you get there. Everyone there? Okay. Now I'm going to copy -R LJ test. And we're going to go to tilde/compute. What this is telling it to do is copy LJ test, all the folders and everything, the folder and everything inside the folder. That's what the -R means, into compute. And that compute is sitting in my home directory. That's what the tilde means. Go to my home directory and then go to compute. And when I execute that, so let me just make sure everyone's got that command, copy -R LJ test into the compute folder. Now I'm going to CD into the compute folder. So let me, there's kind of a shortcut. You can do the same thing. You can go tilde/compute. And that'll say, go to my home directory and then go to compute. And then when I list that, you'll see LJ test should be in there. You probably don't have this other junk. I was just doing some other things in there. LJ test, you should have LJ test when you list it. So anyone not have LJ test in their compute folder?
Okay. Yeah, I'm using the GUI for Mac, and I'm still trying to figure out how to copy it into the folder.
I don't know about the GUI for Mac. Does it have like two sides, like your remote and then your local machine?
Yes, it does. Yeah.
So you should be, let me bring up WinSCP real quick and see if I can. Help you. So I have something that looks like this on mine. This is my local computer. And then this is my remote.
Yeah, that's exactly what I see too. So the LJ test there, can you like copy that folder?
Yeah, so I think if you just hit Control C or copy,
Yeah, okay.
and then you go, the way you navigate this is you go up. That's what this little top thing looks like here. If I double click that, it'll go up to my home directory. Oh, I went too far. Now where am I? Let me go back. Yeah, that's the problem you have, right? Is this is in LJ groups. C group home. Why did it dump us into groups? Now we got to find your username. So it looks like I'm on Z home. What's your username? Ethan?
It's Ethan Gus, but it doesn't look like I have a file there.
So I think, yeah, we'll have to, I don't know why it's going here. They store them under different home directories. So you might have to go to home 3. There. Blue home, let's try blue home. No.
Yeah, I could figure that the thing with the GUI out later. I can just use a Linux shell now. Get it to work that way.
Yeah, let's do that offline. You can contact me and I can see if I can help you.
Okay, thanks.
Let's see home. Yeah, so here's my home directory. Okay. So an LJ test, let me go into LJ test now. CD LJ test. And I think I have this already set up if you list this for what we need to do. So then you can go into this folder. We're doing N500. There's nothing special about this. This is just the default one I set up. And then I've got MD and MC there, but we want to go to MC. And so you want to print working directory. It tells you where you are. So I'm in my home directory. I went into LJ test, N500T08 MC. And then who is not here that can see this red LJ MC test in submit.h? So I went to my compute folder, LJ test, N500 MC.
What's a PWD?
That's print working directory. So if I want to see where I am.
How is that different from like LS?
LS tells me what's inside my current folder. Does that make sense?
Yeah.
So PWD is a common Linux command just to know, oh, where I am. So if I go CD and print WD, it tells me I'm in my home directory. And then I can go to compute, LJ test, 500, MC. So you notice you can actually do this all in kind of one swoop. And then I can LS. Okay. Let me walk through what you see here. The red is an executable. I already compiled it for you. We practiced that last time. I can tell you how to do that again in a second. But I could, if I wanted to, just run this locally. I could run this and then give it the input file like we did last time, but I don't want to do that. I want to teach you how to submit a job so that you can do something longer. So the MC test in is my input folder or my input file. So if I look at that, MC test in, this is where it's saying do 500 particles, 0.85. So similar to what you've already seen before. Notice that I'm just going to do 60 steps for equilibration and 200 steps for production. I think this will take about a minute or so, maybe 2 minutes. I think I made it maybe 2 minutes. So this is very similar to what we ran last time. Now I want to look at submit.sh. Submit.sh is going to tell the supercomputer what to do to run this job. So here's the commands, and let's go through this. I have to have a command that tells me how long I think the job's going to run. And this is kind of the hardest part. You don't necessarily know how long it's going to run right now because you don't have a lot of experience. But I think I set this input file up to run about 5 minutes. So what I often do is I will set my simulation up, have it run for like 100 steps or something like that, and then time it. And then say, okay, it takes about this long to do a step. And so I can, if I want to run for 2 days, I can do 1,000,000 or whatever. You're just going to have to play with that a little bit. This end tasks, notice it says number of processor cores. Modern computers, right? Modern CPUs have multiple cores. And so if I was running a parallel job, I could say, oh, I want to have 3 of the core on that run. Nathan, if you're stuck in editing mode, hit escape and then colon if you're having a hard time. And then Q. Nodes then is the number of actual physical CPUs I need. So if I wanted to run a job that needed 10 total core and I only had chips that had 5 cores on them, then I would have to put 2 nodes and each one has 5 cores. So 2 times 5 would give me 10 core. Now this code does not run parallel. So I just say I need 1 core and 1 chip. 1 chip, 1 core. Does that make sense? That's why these are 1. This tells you how much memory you need per core. And I just leave that at the default for whatever the supercomputer thing gave me. If I go back to this job script, you can set all this here, right? I can say 0 GPUs, whatever. But notice that it said end task equals 1, nodes, and memory. That was just kind of default. What are these other things? You can give it a job name. This is just for use. It can be anything you want. It's just so that you can keep track of your job. So I just called it LJ500MC. MC code 500 particles. You can be as complex as you want. You don't even have to give it a job name because it's going to give it a number if you don't. This is all optional. Everything kind of after these 4. Mail user means if I wanted to email me when it starts the job, that's this. When it ends the job or if the job fails, it will email me. So you have to tell it your user, your email, and then you have to tell it, do you want me to email when it starts, when it ends, or fails? So you can just delete those lines if you don't want it to email you. This, just leave this. It's just kind of default. They need to run some things. You don't need it. But here is where I'm setting up my job. So the first thing I do is I tell the job to go to my compute folder where I have my input and my executable. And so you were already there manually, right? We went to compute, LJ test, this N500 MC. That's the physical place. If I go out and I do my print working directory, this is this part right here, LJ test N500 MC. All this stuff is the tilde compute. So how do you edit again? You go to VI and then submit. You look at whatever file you want. And I'll tell you how to edit in just a second. Once I'm in the directory where my executable is, I run the command. And the command you want to run is, my executable is called ljmdmc. My input folder is MC, or my input file is mctest.in, and then I can name my out whatever I want. Again, we did this line right here just in the command line last time, and it just ran in our current script or in our current shell. But for long jobs, you don't want to do that because you're going to bog down the supercomputer. It needs to batch it out to whatever computer you want. And then the supercomputer likes you to put this little exit statement in so that it completes. You probably don't need to do that, but they like you to do that. So all I'm doing is, it's the computer on the back end, the supercomputer, when I submit this job, it's going to select a computer to run on and then send these commands to that computer. And so what I want it to do is first go to the directory where I have my folder, so my input and my executable, and then type the command to run my executable. So you're going to want to change this email. And so the way you can do that is go to, if you're in VI, you can hit insert, and that will allow you to go into, or hit I, and it will allow you to go into insert mode. And then I can just start deleting stuff and do whatever I want. I don't know what your email is, but student name at byu.edu or .net, whatever it is.
So it doesn't have to be a BYU email?
Nope, it can be whatever email you want. Gmail, whatever.
And we don't have to have that on there. We could just delete those 4 lines.
Yeah, you can delete these 4 lines if you want to. And the way you can delete is you can either backspace them all while you're in insert mode, or if you hit escape and go out of insert mode, then you can just hit double D and it will delete the line. And you can undo stuff in VI if you just hit U. Undo. So I'm going to go all the way back to knots or whatever. So if you have copied everything into your compute folder, notice, I want to emphasize this again. This little tilde means go to my home directory. So mine is not the same as yours. And so this will work for you. It'll go to your home directory and then go into the compute folder and then go into LJ test folder and then go into this folder and then go into the MC folder. And that's where the executable is. And the wall time I have set is, I forgot to say this, this is 5 minutes. So it's seconds, minutes, hours, minutes, seconds. So 5 minutes is what I think this is going to take. I actually think it's going to be a little less than that. It's probably going to be 3 minutes. But the only thing you should really need to change is either delete this stuff about mail user and mail type or change it to your email so I'm not getting all your emails.
So in Python, whenever we put the pound symbol, that means it's not going to see that, right? But that seems totally different in this. That's not what it's doing, right?
Isn't that confusing? So
Okay.
bash right here, that is, it's like Python, right? It's the bash scripting language. It's not Python. If I wrote a Python script, I would have bin Python right here. Then I'd put Python commands down below, but you don't want to do that. Whoops. You want to, this just uses the bash shell. And that's kind of the common shell now in Linux. There's other shells. I think Apple's default one is BSD for its shell. There's a C shell, a TC shell, which have nothing to do with the C programming language.
Okay. And so the reason it's not seeing those other comments, is it because there's just a space after the pound symbol?
It really, what it's looking for is this sbatch keyword.
Oh, okay.
Is really what it's looking for. Bash will look for these, but it's looking for sbatch and then it does something.
Okay.
Okay, here's what we're going to do. So if you've already made your change, you can save that. The way you would save it is do R or W, sorry. W means write. And then if you hit enter, it doesn't exit. But if you do WQ, it writes and then quits. Or there's a shortcut X, which is also write and quit. But WQ is often how people do it. And then I'm going to teach you 2 commands here. There is an sbatch command, which is going to submit this job. And all you do is type sbatch and submit. The whatever the submit script was, we called it submit.sh. I can call it whatever I want. You can call it your name. You can call it Star Wars. You can call it whatever you want. And when I click on this, it's going to submit my job and it gives it a number. And this is all internal to the supercomputer. And I can see my job if I do SQ. And then I want to put my username in, or I'll get all the jobs on the supercomputer. So SQ is SQUEUE. -u means use it for this username, and my username is TAK6. You want to put your username in. Don't put mine in. Well, you can put mine in. You'll just get my job. And this tells me I had something running. I called it LJ500MC. It's running on the M8 node list. And I'll tell you what that kind of means in a minute. It's been running 36 seconds when I type that command, and R means it's running. And so in the background, it's running this simulation and writing all the stuff to file. So there's two key words here, sbatch and sq. Sbatch allows you to submit a file using your submit script. And then sq allows you to check all the jobs you're running. And this one I think takes about 2 minutes. But you see now I'm at 1:19. Let's see. If you wanted to delete a job, like if you submitted it, it was wrong or something like that, then I actually forgot. Let's see. Kyle, do you remember what the command is? Is it sdelete?
It's scancel.
Scancel.
And then just the
job
job
ID.
number. Yeah.
4068131. So I could cancel it if I wanted to. And there's all sorts of Slurm commands. And if you want to learn them, you can go to the supercomputer. They have kind of some documentation on it, Slurm commands. So scontrol, scancel, all this sort of stuff, sq, and then sbatch is the one that we already kind of talked about. But again, you can go here to the job script generator, and you can tell it all the options you want. This is your wall time. You can change it to hours, minutes, seconds, how much memory. You'll want to just run one core or one processor for right now. You don't necessarily need to worry about test or preemptible. Test means if you're doing something short and you really want it to work, sometimes the supercomputer is really full, and so your job won't start for a long time, but you want to test it right now so that it'll be ready. Testing will allow it to run fairly quickly, but you can only go an hour on there. You don't necessarily need most of this other stuff, but notice that you can do I want you to email me at whatever your email is, and then you can put your job name in, and it updates this script to do that. So here's all and then you can just copy that in and then submit your job.
So Dr. Knotts, that's on the supercomputer website, that
Yep.
thing that you're looking at right now? Cool.
Yep.
So if we just create a blank, well, I don't know if that works. If we just create like a blank folder in some directory, can we use the VI command to go and edit it and like paste that code, or how would we get that code into where we need it?
You can use VI. What I would do is, if you're not very familiar with VI, I think Kyle said he uses Nano. I've never used Nano. Maybe that's a little easier because it wasn't around when I was learning stuff. So I've never used it, but that might be easier. But what I would probably do is I would open up, if I'm on Windows, I would open up Notepad or WordPad that you kind of see here. And I would just copy this into there. Control C, normal thing in Windows, Control V. And then I would save this somewhere on my local machine. And I'm going to save it maybe on my desktop. I'm just going to call it example submit. It can be whatever you want. Windows is very, deliberate about file extensions. Linux is not. You can call it whatever you want. And then I would go to my WinSCP, and I can go to my desktop where I save that, example submit, and then just copy it over to my compute folder on my supercomputer. Does that make sense?
Yeah, and so does any job that we're submitting to the supercomputer have to be in the compute folder?
Yes, that's what they want you to do. And there's some advantages to that. Is the compute folder is actually physically housed on disk space that is fast, and your home directory is not. It's a little slower. So if you don't want to be limited, for these jobs, it doesn't matter, but for a big job, you don't want the IO, the file read and write, to limit your job. So that's why you put it on this fast space. So yes, they want you to put it in a compute folder. What else? Anyone else need some help with this? I think my job's probably done. If notice I just push up and it redoes, you can keep pushing up and do previous commands on Linux. So it looks like mine's done. I don't have any more jobs running right now. So if I list the directory I'm in, because I'm in that directory where we wanted to submit it, notice I have mctest.out now. This is the file it wrote. And it also has this slurm out. So that's just, if there's any problems with the job, it'll write it into that folder. I think it also writes any output that was supposed to go to screen, like how many steps it wrote. So you can look at that. But I'm going to look at mctest.out. And remember, you could have called this anything. But this is similar to what we've already seen before. This is the output folder file. It tells us what we ran. That's all the initial stuff. It shows me my initial positions. And you have to scroll past all 500 of those to get down to the iterations. And notice what it's showing for an MC, for this code, I just have it output the pressure, instantaneous for that iteration. So 0, 10, 20, 30. The average pressure over all, because pressure is an average quantity. That's where you want it to be. And then the potential energy. And so I think what did we do? About 200 total steps. And then it writes the final positions so that I could restart from there if I wanted to. And then it does the radial distribution function. So you can copy paste that into Excel or your favorite graphing program. And then it writes the simulation averages for pressure and some other properties. Okay, so you have a job, you have a homework problem that you're gonna wanna run on the supercomputer because it's gonna take like 2 or 3 hours. Because it has you generate a radial distribution function for a certain density and pressure, and it's not equilibrated yet. So you're going to want to run that job, and it's going to take, I actually ran it. It took me a couple hours. I think I tell you how many steps to do and things like that. But to do that homework problem, what you would do is you would create a new input file. And I think the temperature is like 1.8. So I would change this to 1.8. And the density is, I can't remember what it is, but I think it's like I think it's 0.6. And do I tell you, does anyone know, do I tell you how many steps to run? I don't think I do, but you're gonna wanna do maybe like 10,000 equilibration and maybe 20,000 production steps. You're gonna not wanna start here necessarily. You're gonna wanna change this to generate because that initial coordinate was for something else. It was for a different temperature and pressure. So it's not really an equilibrated system. It's not necessarily going to break anything, but I would just start it generate from a new FCC lattice. You're probably gonna wanna change output to maybe every 50. So you're not outputting as much. And I think I say, I want you to go to 4.7 on the radial distribution function. You probably want to change this back to like 25. So you have to run a homework. I think it's homework problem number 3. You're going to want to set something up kind of like this. And if you want to, you could change this to generate seed. And then you're going to submit that job to the supercomputer. And it's going to, you probably want to, I would give it maybe a 3-hour time limit. And then I think that should cover it. Submit it at night, submit it whenever you want to, and it will run in the background. You don't even have to be logged in. I can log out after I submit a job. Okay. Kyle, are you on the supercomputer right now?
Yeah, I am.
Are you using Nano?
I am using
You
Nano.
want to
Yeah.
share your screen and show people maybe they want to use Nano instead of VI?
Yeah, sure. Okay. Yeah, so here's Nano. It's, you know, I guess it's pretty simple. I don't know if VI has these commands down here, but you know, it's pretty self-explanatory. The only thing is, if you prefer this, I do, as it's, you're always in the editing mode. You're not really ever in viewing mode.
Yeah, so there's not two different modes like there are in VI.
Yeah, that's right. I like it. I guess I just, you know, never really got used to changing between the modes.
Yeah, most people don't start with VI anymore. It's just around. And so you just type Nano and then the name of the file to get into it.
Yeah, that's right. And if you accidentally mess it up, then I just, you know, do Control Exit, and then it asks you, well, wait, do you want to save it? And you'll say no, or just N, and that's how you do it.
So Nano might be easy for you than VI. If you want to do that, maybe I'll do Nano next year. Go back in for a second to your Nano. So the carets there mean control. So Control R is write the file, and then Control X is exit the file, I guess. And then
So Kyle, you said you're always in edit mode. There isn't like a read only mode. Is that what you said?
Yeah, that's what I said.
Nano.
which is mostly how you guys exist, right? In your world, like Word, you're always in edit mode. If you type something, it's going to put it on the screen. So here, if you type something, it's going to put it on the screen. Or if you delete something, it's going to put it on the screen, right? Or delete it from the screen. So you don't have to worry about this escape stuff and all that sort of thing. So Nano might be easier for you guys. And you're just using backspace, arrow keys, normal type of editing.
Yeah, I don't know if there's like YJ or I don't know, whatever you guys use to like go around, but yeah, I just use the arrow keys.
And then you can also probably page up and page down in long files.
Yeah, you can see just the Control V.
Control V.
Yeah, Control V, Control Y, and it just tells you what to do all the time.
Okay. Okay, does that help some people? Did everyone get theirs to run? Everyone got an output? Okay. If you are still having problems, make sure you email me and let's get it so you can submit a job. And if you have questions about some Linux, again, there's tutorials on the Supercomputer website. The main commands you need to know are things like CD, change directory, copy, CP. What else did we use? LS, list the directory. And then you're probably going to want to know how to delete a file. Let me bring up my screen again. So if I wanted to delete this slurm.out, I type RM and then the name of the, so remove, it's RM is how you delete something, remove. And I can remove that file. If it's a folder you want to remove, you have to do RM-R. That's that recursive thing because it says remove everything in the file and then remove everything in the folder and then remove the folder. And so let me go up a little bit and I'll show you that. like if I wanted to remove this LJ test that I had in my compute folder, I'd have to put a -R. And then it's not there anymore, or LS. Okay. Then we need to talk about a couple other things with MC. I'm going to go to my other computer. And we're going to, you can do some pretty fancy simulations to get useful properties with Monte Carlo.
So the virial theorem works for both Monte Carlo and molecular dynamics?
Yes. We get the pressure the same way. It's from statistical mechanics. It's not restricted to Monte Carlo or MD. And so, yes, you can, it's used, the same equations used in MC or MD. Okay. Up until now, we've done what are called canonical simulations. Canonical is related to the canonical ensemble. Oh, sorry, a second. I need to get all the way down. Okay, right here. Another way to say that is the simulations we've done is constant N, constant V, constant T. NVT, that's a common term you'll hear. The NVT ensemble or the canonical ensemble. We derive the canonical partition function for a constant number of particles, a constant volume, and a constant temperature. And that's what we've kind of used in MC, and that's what we used when we did the partition function. We used NVT canonical ensemble. What if I instead wanted constant pressure simulations? The variable that you, so basically I want NPT. Instead of setting the volume, I want to set the pressure and let the volume change in my simulation, is what I'm going to do.
How are we fixing the temperature in there?
How in MC, it's very easy because when you move something, you are setting beta, right? Our criteria looks like this, delta U over KT. That T we use, we're fixing the temperature, whatever that is, 0.85. We're moving things with this acceptance criteria when we do MC.
Okay, got it.
So MC is actually very easy to set temperature. It's hard to do constant temperature in MD that we'll talk about in the next chapter. But how do I do a constant pressure simulation? And because this is very useful when we want to do phase equilibrium. We usually set the pressure like we exist at atmospheric pressure, or in Utah, 0.87 atmospheres or something like that. And then we want to see what happens. Well, what I have to allow the simulation to do in this case is I have to let the box move. The box will either get bigger or smaller as I move around. I have to create a new Monte Carlo move. I'm not just going to move particles anymore. I'm going to actually let the box size change. And so a little statistical mechanics is to let the box change. That means I'm actually changing the partition function a little bit so that now I don't have to take into account just the change in potential energy, the delta U part. I also have to take into account the PV part, the PV work of changing the box, or the total energy of the system. And so usually we would not have this term in there, right? There would be no PV term in our partition function. But if I let the box change, it has there's a new partition function. And it actually proves this in chapter 5, I used to have students prove this as a test problem, is come up with this. And they have to do the canonical partition function. And then I decided I didn't want to do that anymore. But just to make sure you understand, we used to say the probability in the canonical ensemble, NVT, is something like e to the minus beta u over z, the partition function. Well, now you still have that e to the minus beta u, but you also have this part about the PV work. just to kind of give you an analogy here, right? We change our ensemble, so we had to change our partition function. And it's kind of a natural, it looks fairly natural once we do it. It has some PV work in it. And when we do our metropolis acceptance criteria, you need to put a little parenthesis right here. This is now total energy. It's the PV plus the U. It's not just delta U anymore. I have to do this whole sort of thing. Because you remember the way we got that acceptance criteria was we put the probability of the old over the probability of the new, or the new over the old, and the Z part canceled out. And so I'm calling the total energy part. There's the potential part that we used to do. And then there is the PV work part. But all I have to do, it's fairly easy to change my Monte Carlo simulation to do this, because I know how to calculate volumes, and I know I set the pressure, and I already know how to calculate potentials energies. So what I do is I just create one new move. It is a volume change move. I randomly say, I'm going to pick a random number, and I'm going to randomly, and it has to go, remember, this is going to be between 0 and 1. And so when I multiply it by 2, it's between 0 and 2. And then when I subtract off 1, it goes from -1 to 1. So this gives me either it's going to increase or decrease a volume size. And I set some max volume decrease or increase, similar to where I set a max position change on my old moves. And then I either add or subtract that from my old volume. So I just randomly propose a new volume. It could be a little bigger, it could be a little smaller than where I was. Okay. Then I have to scale all of the positions. Because if I made my box a little bigger, then there'd be kind of some void spaces, right? If I had my particles all in here, and then I went to a bigger box, I actually want to move these particles out a little bit compared to where they were. And the way I do that is, this is called the scale factor. I multiply everything by the scale factor, which you can kind of see, right? The cube root of V new over V old is really just, it gives me, the cube root gives me the length of a box, because this is cubic. And then I just scale it. If I increase my length, I scale everything by the fraction I increase the length, or if I decrease it, then I go down a little bit. And so this just says, after I propose a move, I got to shift all my particles, or scale all my particle positions. So there's my frequency, and then I just or my scaling factor, and I multiply it by all the old positions. And it's kind of shown right here. And then I do my normalist metropolis criteria. So let's walk through a couple of the things we had to change to get this code to work. Instead of just calling one type of move, remember we had a move that was an atom displacement. That's what we've done so far. Now we have to occasionally call a volume change move. So I have to add a little step in here. This is actually a fairly easy step. I randomly pick a random number between 0 and n, or the number of particles I have. And then whenever it's equal to 1, I'm calling a volume change. So how often does a volume change move get proposed?
Once per every time you've checked every other molecule. So
yeah, so it's not very often, right? So if n is 500, I'm saying I only want to call a volume, or have a chance to call a volume change, one every n steps, if that makes sense. The way this is going, I'm going to call particle displacement moves way more than I call a volume move, if that makes sense. Now we got to figure out what V change does. So here's what V change looks like. I've got to keep track of the old and the new energy, the old and the new volumes. And remember, there is a subroutine called energy that just calculates the energy of the system. We've been using that for a long time. It loops through all the particles, calculates all the Lennard-Jones, and returns the energy. We had to do that for the normal particle displacement move. And so I haven't changed anything yet. So when I call energy, that gives me my current or old energy. And I know what my old volume is because it hasn't changed anything. I know what the lengths are. I know what the old positions are. Remember, it's called cube. This is L, and this is L over 2, which is cube old 2. So I just save my old positions and save my old energy in a variable. Okay. Then I randomly generate a new volume or a new displacement, a new delta V. So I'm either going to increase or decrease the volume a little bit. And so then I need to calculate a new L for this new volume, and then the scaling factor. I saved my old cube length or my box length. I have my new box length. Here's my scaling factor. I also get my L over 2 for the new positions. And then here's where I'm just scaling all my positions. And then I have to calculate the new energy. Notice this is all saved in the arrays for my positions. So when I call energy again, this gives me my new U. And this was my old U. So it's going to give me my delta U for this move. Now, if I change volumes, I also change the long range correction to pressure. We talked about the long range correction last time. So this is my P correction. I have to keep track of the old one and the new one. So here is my delta energy. I also have old, I also need my old correction, my U correction. Those corrections, if you remember all the way back up, actually, I'm not going to go up there right now. Remember the corrections though are basically based on the box length, the R cut and the box length. But if that's confusing to you, just kind of forget that for a second, but just know that I do this line is beta delta U. This line is P delta V plus the log V over V part. And I take the exponential of it, so the log goes away. Or sorry, this is just the P delta V part. This is the log V over V part. So all of these DEs just sum up this thing right here. This is my new acceptance criterion. It's giving me exponential minus beta delta U minus beta delta V, and then this log V over V term. Okay. But then I do the normal thing. I check to see if a random number is less than the exponential of that. Does it accept it? If I do accept it, then I can go on with my simulation. If I reject it, I have to assign all the old properties back so that I keep the same state. Does that make sense? Similar to what we did with a particle displacement. We randomly pick a particle, we randomly move it, we calculate the delta energy, and then if we accept it, then we go on with the simulation. If we reject it, we got to put in the old stuff and before we go in. So I hope you kind of see the general idea here. It is we're doing something very similar. Instead of generating a particle displacement, we generate a volume displacement. We do have to move all the particles because of that, because we changed the volume. But then we have another acceptance criteria. We calculate the change in the total energy, which has a U part and a PV part. And then we accept or reject. Now,
Do you only have to care about that PV term when changing the box size? Like for all the other moves, do you just compute as normal?
Yes. And so this is just for the box size. Well, for the other move, your V old and V new would be 0. So this part would go to 0, right? Because I didn't change my volume. And this part would go to 0 because it turns out to be the same. It just comes out to be delta U. It's only when you do a volume change that those are not 0, if that makes sense. So if you look in your acceptance criterion up here, oh, come on, erase. If you look at your acceptance criteria here, then if I don't change volume, this goes to 0 and this goes to 0, and you recover just your normal metropolis criterion where I move a single particle. Does that make sense? Okay. Now, you have a workbook that does this NPT simulation. Let me share my other screen. It's called Isobaric Ensemble or Isobaric NPT. Let's see what it's called. I thought I had it up here already. Excuse me, Isobaric, oh, mercy. Isobaric MC simulator. Oh, and it looks something like this. I can change the number of molecules. I can change my initial density, a guess of what I think it should be, set my temperature, and set my pressure. These are all dimensionless quantities again. And when I start this simulation, it's going to show me my energy plus my density. It's not outputting pressure anymore, it's outputting density because it's doing this metropolis criterion to set the pressure to 3.6. And so that means my volume is going to change. And these take a long time to run. So when you're doing these simulations, you got to plan for a little longer time than you normally would. And you can see it's equilibrating out, that energy is going down, but my density looks like it's going up. So for this pressure, 3.6, it looks like my guess for initial density was not high enough. I wanted to guess something bigger because it looks like now it's out to about 3.3 or 0.3, keep going up maybe to 0.4. But eventually this will equilibrate out and I'll figure out what density corresponds to the pressure I set. Constant isobaric, constant NPT simulations. Now these are cool. We use NPT simulations a lot in molecular simulations because when I'm doing a protein simulation, the way I do a protein simulation is I get the protein in my box, then I have to put water around it. And the way I put water around it is I have another box of water that I've already equilibrated, and then I delete anything that's overlapping. But it creates void spaces, if that makes sense. Because I delete everything, so the water is not really equilibrated around the protein. And what I want to do is I want to make sure it equilibrates to the constant pressure, the right pressure. And so I run an NPT simulation at 1 atmosphere or whatever my pressure of my system is to figure out what box size I need. And then once I know what box size gives me that pressure, I'll convert over and start running NVT because NVT simulations run faster and they're more stable, if that makes sense. Okay, I'm going to let that run in the background. You can let yours run too. But what this is doing is it has 125 particles. On average, it runs 125 particle displacements and then 1 volume change. Move 125 volume or particle displacements and then 1 volume change. Okay.
So am I remembering correctly? You said that your Monte Carlo simulator I guess, pre-calculates what the box dimension should be for a particular pressure?
That's right. Well, no, what it does is you give it a density. So you give it N and V, so to speak, and then it will give you whatever pressure corresponds to that. So you don't necessarily know what the pressure is going to be. Does that make sense?
Oh,
It's going
okay,
to
yeah.
calculate that. Here, I'm giving it a pressure. I don't know what the density is going to be. You give it an initial density to kind of start, but then you'll notice that I was way off. It looks like now it's starting to kind of equilibrate above 0.5. Maybe it's going to start bouncing around the correct density now, if that makes sense. So let me just kind of talk about that for a second. There's kind of canonical variables or variables that match. If I fix pressure, my volume has to change. If I fix volume, my pressure is going to change. And so that's what you see here, the balance. If I fix the pressure, the density is changing because the volume's changing, or vice versa. What if I want to fit, I can either set potential or total energy to be constant, or I can set temperature to be constant. Like Newton's equation of motions, it conserves total energy, and you get whatever temperature comes out of that. The particles, right? If I start with all potential energy, a ball on the hill, and then it starts rolling down into kinetic energy, then I can calculate out whatever temperature of the system that would correspond to. But I fix the total energy of the system, I get temperature. Monte Carlo does the opposite. It fixes temperature and does constant energy. And it's not dissimilar to what we do in experiment, right? If I want a constant temperature experiment, I have to create a bath and let the energy exchange between my sample and that bath. I stick it in like boiling water, or I stick it in sort of freezing water, or whatever bath I have, whatever bath temperature I have. And so there's a canonical variable swap between kind of pressure and volume, between energy and temperature. And there's one other one I want to talk about: number of particles and chemical potential, or the Gibbs energy. Because when I do an VLE experiment, if I want to see the two-phase region, what I'm saying is that the chemical potentials or fugacities are equal in each phase. How do I let the fugacities get equal? I let the mass move around. And so the last thing I want to talk about, and we're probably going to have to do it next time because we don't have much time today, but I want you to read about it, is called Gibbs ensemble. Let me share my screen for a second so I can write. I want you to read about this in the book before we talk about it next time, and that'll help you kind of firm up a lot of what we talked about. But Gibbs ensemble allows me to simulate two boxes at the same time. And they're at different densities, where one would correspond to the liquid phase and one would correspond to, say, the vapor phase. And the way I get my chemical potentials to be equal is I have three types of moves in my simulation. I have a normal particle displacement, a normal move in each box. I then have a volume displacement like we just talked about, but I couple it so that if I propose this one gets bigger, this one's going to get smaller. So the total overall volume is conserved, but I'm allowing it to change between the big box and the small box, if that makes sense. So I'm allowing the pressure to be the same with each box. And then I have a new move that we're going to talk about next time. I have a particle transfer move. I'm going to randomly pick a particle and randomly put it in the other box. And I have to create a new acceptance criteria to do this. But what this allows it to do is the chemical potential between the boxes can equilibrate. The mass is allowed to go where it wants to go based on the pressure and the temperature I give it. So it actually takes a long time because I have to keep track of two boxes at the same time in my simulation. But I'm randomly moving particles, I'm randomly getting bigger and smaller, and I'm randomly transferring particles. And that allows me to do mu PT. We call that the grand canonical ensemble. But what we're fixing is chemical potential, pressure, and temperature. We're enforcing the chemical potentials to be the same in each phase. And if I let this run long enough, then I'll get a system that has a high density, which will be the condensed phase. And then I'll get a phase that is small, which is the low density vapor phase. And it allows me to start figuring out the two-phase envelope in a system. I can do vapor liquid equilibrium. So make sure you read through this Gibbs ensemble. This is called Gibbs ensemble.
Dr. Knotts, can either box end up as the liquid, or did you change some setting to kind of force one to be the liquid?
No, either box could end up at the liquid. In fact, there's a Gibbs ensemble simulator that you can run, and that we'll run next time, that you'll see the box identities shift. There's nothing that forces this one to be the vapor and this one to be the liquid, because I could maybe transfer a bunch of particles into this one, and then this box might get smaller than this box. But eventually, if you let it run long enough, if you're in the two-phase region, one will have a high density, one will have a low density. If that makes sense.
Nice. So it'd be a way to kind of sense two-phase region.
That's right.
And then
If you're in the one-phase region, if you happen to give it conditions that are in the one-phase region, then the two box densities will be the same. If that makes sense. And we'll show that next time. And so read through that section in the book. You should be able to do most of your homework. There's only one homework that requires you to do Gibbs ensemble. I think I made you do Gibbs ensemble, but you should be able to do all the other homework. And so make sure you're working on that. Make sure you have speak questions. One of them makes you do a little coding. So you want to start on that a little early and talk to me if you need help on how to implement that, but it's not a lot of coding. And then the other two are just running the simulations we've kind of already done. You probably already did the first two. One of them you got to run like we just ran on the supercomputer, and then one's Gibbs ensemble. And so next time we'll go for Gibbs ensemble, and then we will let you have time to work on your homework to finish up anything that you have questions on. Okay. Okay, thanks everyone. I think it's devotional time. And anyone have any final questions before we go?